Thank you so much for joining us today. Welcome to the RStudio Enterprise Community Meetup. I'm Rachel. I'm actually calling in from San Diego today, so more of a morning meetup for me. We're streaming out to LinkedIn and YouTube right now, so I'd love to have you all introduce yourselves and where you're calling in from in the chat. I'm excited to have Matt Malloure here with us today for part 2 of our Functional Data Analysis Meetup series. A big thank you to Santiago, who kicked off the Intro to FDA meetup initially as well. I'll share the link to that recording too, so you have it as well. If this is your first time joining one of these sessions, welcome. We're so glad to have you here. This is a friendly meetup environment for teams to share use cases, teach lessons learned, and just meet each other and ask questions. I just wanted to say this as well. While it's called the Enterprise Community Meetup, this is open to everyone, regardless of where you work and the tools that you use. I created this group as the Enterprise Meetup so that it would be okay for us to occasionally talk about the RStudio professional products like RStudio Workbench and Connect. But everybody is welcome. Together, we are all dedicated to making this an inclusive and open environment for everyone, no matter your experience, industry, or background. I'll share a link in the chat where you can find out about other upcoming events too. Also, during the event, you are able to ask questions. You can ask them through the chat. If you're on LinkedIn and YouTube, it will gather them for me. And you can also ask questions anonymously through Slido. And you can just use the link that I'll show on the screen here in just a second to be able to ask questions anonymously as well. With that said, I would love to introduce our speaker for today. Here, let me put us side by side. There we go. Awesome. So I'm so happy to be joined by Matt here. Matt is an associate research data scientist supporting new product development within the packaging and specialty plastics business at the Dow Chemical Company. And Matt and I actually met through Santiago's FDA meetup, which was your first meetup, I think. Mm-hmm. Right?
Yep.
Awesome. I wanted to share that too, just to say if there's ever a topic or use case that you all would like to highlight from your team, we'd love to hear from you too. So if you ever even want to just float an idea by me, please feel free to connect on LinkedIn or email me too. It's just rachel@rstudio.com. But I'll share my LinkedIn in the chat as well. Okay, that's enough for me. I'm done. Thank you again, Matt. I would love to turn it over to you, and I'll pull your slides up here.
Awesome. Thanks, Rachel, for the introduction. Thank you all for joining. I'm excited for this opportunity to just continue the discussion on functional data. So during, I think it was in March with Santiago's meetup, the Q&A session, two topics came up: functional PCA, principal components analysis, and functional regression, both of which that I've applied in various projects at Dow. And so that's why, connecting with Rachel, we said, all right, let's go for part 2 of the series, and hence we're here today. So I've broken this talk in general into, I guess, 4 major sections, sort of an introduction, both of myself and just kind of a quick refresher on functional data analysis, and kind of introduce our simulated case study that we'll walk through and the questions we want to solve using functional data methods. Then second, again, it'll kind of be a refresher with some data pre-processing steps for FDA, so particularly smoothing with penalized splines to create the true functional observations that we want to analyze. And then again, the two topics du jour, functional PCA, which will help us answer the first question about clustering different additives or experimental materials based on decay curves that we see for measuring a material characteristic. And then functional regression, so then taking those characteristic profiles to predict an application performance. And I think it'll be important in that section as well to kind of compare to traditional or other methods that we might use to analyze such data given various limitations we'll talk about, as well as just the a tall versus a wide data matrix. And last, of course, just some summary and takeaways. So quickly about myself. So I'm native to Michigan, which global headquarters for Dow is in Midland, Michigan, but I actually work in our Texas location, and you'll see why here in a second. So Metro Detroit is where I was born and raised. I didn't travel very far to do my first 2 degrees. So Grand Valley State University is located in the western side of the Lower Peninsula, just outside of Grand Rapids, Michigan. So I did my bachelor's in stat and master's in biostat. And even though the master's program is technically a terminal degree for most, I still wanted to learn more. I also realized that I wasn't a fan of cold and winter, so I came south, where I've still been. So I went to Texas A&M University for my PhD, which is also a connection with Santiago, as he was also an Aggie. In my PhD research was kind of a grab bag of a bunch of topics. So Bayesian nonparametric goodness of fit testing using cross-validation Bayes factors. It's essentially the use of kernel density estimators for an alternative for our alternative hypothesis in multivariate goodness of fit testing, like testing multivariate normality. And it required some data splitting and divide and conquer type techniques for cross validation. So for those interested, so I'll throw in a shameless plug. One chapter of that work is published in International Statistical Review for those interested in checking it out. So after graduation, I went from College Station to Lake Jackson, Texas, just south of Houston, where so I'm coming up on my 5-year work anniversary, but all but like 2 months of time, I was a statistician within core R&D, so supporting global R&D at Dow in any and all statistical needs, primarily in experimental design. And just recently, I took the role that I'm in as a data scientist in packaging and specialty plastics, and that was a natural transition because my primary focal point was the plastics business. So it was just taking a step to do more projects within the business. My general specialty areas, especially at Dow, so hence today, functional data analysis is probably my main area at Dow, in addition to nonparametrics and statistical computing or simulation. For project applications, also related to the case study we'll talk about today, is polymer or new product resin design using some machine learning models or computational methods, as well as then development of sustainable products, which is a big push in the industry today, especially with the plastics business. So let's quickly recap or review functional data and functional data analysis. So we're all familiar with the 2 major types of variables: continuous, categorical, or our usual scalar approaches. Functional variables are where we can't use a single value, or we don't have a single value to measure the characteristic of interest, that variable, for an experimental unit. So we actually have an entire process, a distribution, or a curve. And so we want to be able to have a class of methods that allow us to analyze functional variables. And here's some examples. These are all available in the FDA package, which all stem from Ramsey and Silverman, who are sort of the original Bible, I guess, of functional data analysis. Is the book of the same title, published in the, I guess, first time in the mid 1990s. So these examples, you can find this data within that package in R. And common examples. So top left, growth curves. So those of you who have children or remember going to the pediatrician as a child, right? There's unequally spaced milestone visits, but we want to track how individuals grow from birth all the way till 18 years. So for each person, they have an entire growth curve. The Canadian weather data, which, if you recall, Santiago talked about quite a bit. So for, I think it's 35 weather stations in Canada, we're looking at the temperature profile across an entire year for each of those cities and trying to analyze how do the profiles differ, say, based on region in Canada. Functional data can be 2-dimensional or multidimensional. So an example is writing on an electronic pad the letters FDA in cursive multiple times. So you have this also spatial orientation. So it's not required, it's rescaled to time, but it's also, you're not required to have time, say, as your only dimension or your domain for your functional observation. And lastly, something that looks like distributional data, which you can see maybe some challenges in analyzing this, as it has to do with pinching your thumb with your forefinger and the force exerted. And so you can see that there's different time points at which the force starts, and the peak force occurs at different time values in the interval from 0 to zero point 0.3 seconds. Plus, it has a different height as well, so it's shifted as well as scaled. So we won't talk about it today, but registration and alignment as another pre-processing is very important for data like this. Say maybe peak aligning is something you might look at. Now, for analyzing functional data, there are many of the methods that are just analogues to traditional scalar approaches, two which are sort of more unique to functional. Well, curve estimation or smoothing. Certainly, you need more than one point to smooth a curve. So that's a pre-processing step that we'll look at. I think one interesting one is the analysis of derivatives. So for growth curves, you could look at acceleration functions because you've now got a smooth and continuous variable observation that you can take derivatives for. So you get functions, derivative functions, as opposed to just rise over run calculations. Um, for the functional analogs, just so within exploratory data analysis, means, variances, correlations, you can compute all of those. You can do principal components analysis, linear or generalized linear models, and you can even do functional experimental design. And many of these are related, but I think we'll see just natural extensions of methods that we know and love to apply them to functional observations. So to sort of motivate, use cases for FDA. So this is our case study data that we'll talk about. Now it is simulated, and in the link that Rachel, I think, sent out or will send out, I've made the slides as well as my code available. So every analysis, every picture that you see, including all the seeds, is available to explore, and you'll be able to reproduce everything. But for this example, we have 41 different additives, different experimental materials, one of which is a standard. You can think of standard as it could be the gold standard on the market, it could be a control, it could be just a theoretical target that you want to hit. So that's the solid black. But the further study on 41 different additives could be resource intensive. So the idea, one of the questions we'll look at is how can we quickly select profiles or new materials for further study that are most similar to this standard. Now, this material characteristic, it's measured over 24 hours, but it resembles exponential decay. And so, as we might often see, especially with like decay functions, that the time points at which we measure are unequally spaced. So it starts out condensed at time 0, which they all start at 100. So time 1, 2, then it goes every 2 hours till 8, then every 4 hours till 24. So they're unequally spaced time points. And also in the example that we had, based on the data processing to actually create these profiles, we actually had a lot of missing data. So not all that, actually rarely did we have all 10 points. So we had on somewhere between 5 and 8 points for each curve. So each observation, each material had unequally spaced points and a differing number of points. So the first question that we'll ask and try to answer, and this will be used with functional PCA, is can we pick 3 to 5 experimental materials that are top candidates for further study? And second, this material characteristic, this profile, is strongly related to application performance. So as we try to create and design new materials, we'd say, okay, from this profile, we'd also want to know which ones to look at based on predicting performance in the final application. And that's where we'll look at functional regression. Now you might think we've seen pictures like this quite often for some traditional analyses. So some things that we might use, maybe to not answer these exact questions, but to analyze this data, is you could use time series, repeated measures, longitudinal data analysis, all sort of similar flavor. They answer different questions, of course, but we could do moment-based regression. So try to summarize these profiles into some set of scalar moments and then just apply like typical linear models. Or we could do a multivariate approach. So PCA or PLS, say if we had multiple correlated responses. And so we'd actually analyze the data matrix formed here. But each of these have some limitations. So particularly a time series repeated measures, typically you require equally spaced time points and the same number of points for each curve. So a consistent domain for the discrete measurements. For moments, we know in dimension reduction, typically we lose information. So that's always a kind of a pro and con. It's easier to analyze, but we do suffer information loss. And methods like multivariate, so the PCA, PLS, well, that looks at data matrix, which kind of ignores the functional relationship between the successive columns. And in fact, with PLS, it's known, right, that if you permute the columns of your data matrix, you're going to get the same model in the end. So that functional relationship is essentially destroyed and are not captured in these multivariate approaches. But FDA methods allow us to alleviate or basically remove many of these limitations. So I'll pause here for, I guess, any quick questions just about the what is functional data or the case study.
I don't see any over on the Slido yet, but just wanted
Okay.
to remind everyone, if you do want to ask questions anonymously, you can do so using Slido, and I just put the link in the chat. I'll pull it up here on the screen again too.
And there will be more pauses too. So if there's none now and they come up as we go, we can always answer questions about the topics kind of retroactively. No
Sounds
problem.
good. Sounds good. We'll wait till the next question break then.
Okay. So and once you have measured your functional observations, I think what you've noticed is that it's not truly a smooth continuous function that we're analyzing, because we never actually observe this true process because we measure it at set time points or points in the domain. It's always a discretized function. So that's why smoothing is often the first step of pre-processing, and in many cases it can be a requirement for like PCA or full functional PCA. So why do we have to do this? Well, again, with a discrete curve, so X is actually our true process that we want to explore. But we actually observe Y because when we go to measure the points, we try to measure at different TJs the value of this process. There's error likely involved, measurement error, process error. Um, and so we don't observe the true process. We observe something with error that we need to convert to our functional observation to analyze. And so the common approaches are penalized splines in some fashion, Fourier series for periodic data, cubic B splines, or some other regression spline for non-periodic data. We play with the bias variance trade-off with a smoothing parameter lambda. And an important note is that you could do this all at once. So you could take all your observations, smooth them all together, or you can actually treat them and do them individually, which we'll see we have to do in our case. And just to give an example of this, the penalization and smoothing here. So I've generated from the sine function some points. So the gray circles, I think it's 100 or maybe 200 points within the domain -3 to 3, equally spaced. So you see that there is a process underlying this. There is a functional relationship across these points, but we don't have a great, we wouldn't want to connect these points. So how do we actually estimate the true function, the black curve? So if we pick a lambda that's too small, we undersmooth. And as it approaches 0, you basically interpolate the points. So you have high variance, low bias. So we probably wouldn't want to use that red curve. Green, if we pick a lambda too big, we oversmooth. So we actually typically will miss valleys and peaks, which you observe here. So here we have very low variance, but high bias. So the best is, we can pick this through trial and error, some cross-validation technique, but when you have an appropriately smoothed function with Fourier series, you see it's actually hard to discern the blue dashed line compared to black, which tells us that, see, we were able to use splines to capture our true, the underlying process here. Now, how does this apply to our case study data? So remember, we do have the unequally spaced and differing number of points. So we'll do it individually one at a time. Remember, we only have 5 to 8 measurements, but because of using the penalized splines, we can have great flexibility with 20 cubic B splines. So we actually have, like 4 times as many splines as we do points. But we can still estimate the function. We do it one at a time and then reevaluate to basically form a consistent data matrix. So we fit the smooth, evaluate it at every hour time point, stack them all together. You get a 41 by 25 matrix, where row per row, each row is a experimental material, and then eventually we'll kind of re-smooth or reapply the same smoothing to create a functional data object with all 41 curves. So it's kind of like 2 different sets of smoothing, and if you check out the code, you'll kind of see how this works. But we need that functional data object for later use. And how well does this work? So here's the example for the standard. So the discrete curve is actually the dashed red. Applying these splines and reevaluating and plotting, you can see that even with only, I forget how many we have on the standard, 5 to 8 points, the smooth can actually estimate that true or our underlying process very well. And we apply the same approach to all the curves, and I think you can see that we do reasonably well at capturing just the overall shape of each of those individual profiles. So now the question becomes, how do we address the 2 questions? So I guess a short section, if there are any questions, we can take them on the first 2 topics.
One question that was on Slido was, what made you first interested in FDA?
Great question. I didn't cover it in the bio. So before, one of the elective courses at A&M was, I forget the number, it's not important, non-parametric curve estimation. And because of where my research was heading, it was an elective that my advisor said I should take. And so in that class, the professor taught us FDA. So it just was one of those kind of like, happy accidents that my advisor had the project and said, take this class, and we did FDA. So actually, and a part of that class was a project that you had to implement all of the methods. And so I did a study of statehood obesity curves, so actually growth curves, to look at what are the important factors that would relate to like statehood obesity, and test out hypotheses about, socioeconomic status or other information from demographics.
Thank you. A question I had actually is, what's a good way, if like we're just learning about this right now, what's a good way for us to know a project could use FDA analysis?
Yeah, so I think there are some more like natural scenarios where it's just like, when you have one experimental unit, one thing in your study that's got a measurement that's like, I have an entire distribution. I have like, where it's not a single value. So there might be an underlying, like, that, uh, so like a molecular weight distribution. We know that there's not just one polymer chain of constant length. So you have to actually look at like chromatographic data in analytical science or different characterization groups. This is something that you use the same type of methods, you just know you're going to get a distribution. Or if you're looking at growth or decay functions, like it kind of just naturally, you ask the question, can I represent this as one number, or do I need all of these values? And of course, it's like 2-dimensional or more, they might be more difficult, but it's usually like you have something measured over time and space, and it's hard to summarize it as one single value.
That's really helpful. Thank you. I see that we have a question in the chat as well. And it was actually Santiago who said, "Hi, Matt and Santiago. Great job so far, by the way. What is your decision framework for which basis function? Cubic, you can read it there."
Yeah, so yeah, that is a good question. I think the first. Okay, so it's like a tree diagram. The first one you look at is, okay, do I have periodic or non-periodic data? Periodic meaning that so if I look at the function, the far left point and the far right point should be the same. So like the temperature profile is an example where December 31st and January 1st are far more related, even though they're at the opposite ends of the domain. So those temperatures should probably be close to each other. And so then you use Fourier series. Cubic B splines, I think that's just a good default. I know there's some theory out there, that comes from De Boer, that says cubic B splines with a knot at each data point is the best you can select. I think it's more so like you could use wavelets as an example for when you have really peaked functions. And so yeah, like there's a response that I saw. It really depends on what you're trying. Depends on the data you have and what you're trying to do. Because if you think like take some normal distribution, which kind of looks like some of the basis functions in the interior, and you try and have a really peaked function. So like GC mass spec data, which is very peaked. Well, you're going to always underestimate that because the normal just can't get all the way up to an absolute value looking function, but wavelets have that ability. So it really based on the context and what you observe with the data. But a foreshadowing answer is that sometimes you can actually use your data to define basis functions for later use. And that we'll see in FPCA here.
Awesome. Can I ask you one more question?
Sure.
Okay. I see that Ravinder put a question to the YouTube chat. Great question. Is functional data analysis related to functional programming?
I actually don't know the answer to that one. I'm not familiar with functional programming. So I guess maybe I'll ask help from anyone else on the line that might know enough about functional programming.
Yeah, definitely.
Not familiar, so I won't even take a stab.
And feel free to, anybody who's listening, to comment in the chat or share links that have been helpful for you in learning as well. I love getting to see the conversation that happens there in the chat too. But thanks, Matt. I will go backstage.
All right. So to the first question, remember we want to identify three to five values or experimental materials most similar to the control. So to do that, we're going to use functional PCA. Now I mentioned that their functional methods are often analogues of traditional. So a quick 3 bullet point review here on traditional PCA. So we have a data matrix, many columns, likely correlated. So PCA first is a data transformation. It's a rotation to convert those correlated columns into uncorrelated linear combinations of those original vectors. And we can then do dimension reduction because the rotation is such that the first principal component explains the most variation, followed by the uh, next most important, uncorrelated to the first, and onward. So oftentimes we can take many dimensions and reduce them down into 1, 2, or 3 that explain 90 or 95% of the total variability in the system. Mathematically, to do this, it's an eigenanalysis. You compute the eigenvalues to get your PC scores, and the eigenvectors define our linear combinations. And we do this on either the covariance or correlation matrix. So what is functional PCA? Well, mathematically, I guess I'm going out of order here. We also still perform an eigenanalysis, but this time on the functions. So slightly more complex, but the same general approach. We still capture the primary modes of variation in successive order, first, second, third. But now the functional PCs are orthonormal functions, so similar properties to what we get in the linear combinations in traditional PCA. Now, I think this is one of the interesting additional pieces that we get from functional PCA is this idea of empirical basis functions. So Carhoon and Loev have this expansion, and basically what it says is that any functional observation in our set, our sample, can be written as the mean function of the sample plus a weighted sum of the functional PCs, our new building block, and production that I think is pretty powerful.
I think I lost your audio for a second, but that maybe was on my end. I just want to confirm that everybody can hear Matt okay.
Am I?
Nope, you sound fine to me now, so maybe it was just a glitch.
All
okay.
Right. So let's actually apply this to our case study data. So
it seems like it was just the last 30 seconds that we maybe lost you for a little bit.
I'll go back to the expansion. So, okay, why this Carhoon and Loev expansion? This actually gives us our empirical basis functions. So we can use our sample data to make new building blocks, which are these empirical basis functions. So what it says is that any sample in our any functional observation in our sample can be written as the overall mean function, y bar of t, plus a weighted sum of the functional PCs. So we have the PC functions, the XCs, times coefficients, which start originally as your PC scores for the actual observations we observe. So what does this look like? For our case study data, we have the overall mean function, which resembles, our typical exponential decay for all of our samples. And we get two PC functions. First one explains 96.5%, the second 3%. So in two PCs, we basically capture all of the variability, 99.5%. They're not the easiest to interpret, but we'll see in the next slide that we can get a picture that makes them easier to interpret. Another bonus over traditional PCA, often those linear combinations are difficult to interpret in context, but we can actually get an idea of what these PC functions look like and how they contribute to the different functions we observe in our sample. And we can still get a score plot. We have two dimensions. So we actually see that they're not, we don't see just a random scatter here. We see a kind of a parabolic shape, but they are uncorrelated with each other. And so now, just thinking about how we might solve the question with typical PCA, I think we can already see that we have PC scores in two dimensions. Maybe we just perform simple clustering to solve our question. Now, before we get there, so this interpretation idea. So this, if you create a functional object in R that's a result of functional PCA, and you just plot it, you just use base plot function, you'll get this picture by default. And it really helps with interpretation because those PC functions are essentially perturbations of the mean. So what does that mean? Take PC1 here on the left panel. The solid line in each picture is the overall mean curve. Then it takes, so the line defined by pluses is a positive coefficient multiplied by PC1 added to the mean function. So it says for a positive PC1 score, you would expect the shape to change in that way. So it becomes sort of like an increase with a slower decay. A negative value of the same magnitude gives you the minus line. So it basically tells us that, okay, the difference in these three curves really is in the first half of time. The relative steepness of the initial 10 to 12 hours, because essentially after that point, the lines are roughly parallel. PC2, remember, is uncorrelated to PC1. So it would make sense that we basically have, regardless of that magnitude, there's no change or minimal change in the first half of time. So PC2 actually explains the relative decay, the steepness, the slope of that decay in the second half of time. So this is actually really sort of powerful just to get an idea of how those PC functions relate to your overall data as a function of that like expansion. It's pretty interesting, and it can really help to explain the scenario, I think. As dimension reduction, so let's also look at these building blocks to show, so how you could actually okay, once you do FPCA and you define those PC functions, they're fixed, they're known. That's why you can use them as basis functions. The only thing that and the mean function is also known, right? So the only thing in that Karhunen-Loew expansion that changes now are scalar coefficients. So that can be pretty powerful for just dimension reduction, because curves are more complex, more degrees of freedom to change those shapes compared to just, say, two coefficients here. So how this works, we can basically generate new scores to look at the intuition of, okay, how, if I change the coefficient, how does the resulting function shape change? So I've just plotted again the two PC functions. They look pretty flat because the scale has changed. And I'll just generate new pairs of scores. So this one's about 50 and minus 25 for X and Y. So 50 times blue gives me my dashed blue. Minus 25 times red gives me my dashed red. So that's the contribution now, the weighted contribution of PC1, PC2. Add that back to the black mean curve, and you get this maroon function. So it looks like, right, so that for positive PC1, negative PC2, it has a higher, or it's pulled away, it's above the mean curve. It's sort of, the decay is slower compared to the mean. Do this again, all the past results are going to be grayed out, but now see our points over here at a sort of negative PC1 and roughly 0 PC2. So now we see that that shape, which we'd expect, right? That as PC1 got negative, the decay at the beginning was greater. It was quicker, steeper. So matches what we expect. And we can keep doing this again and say 100 times. And what we see is basically now those scores, when we constrain them just to basic box constraints, minimum and maximum from our sample, we can actually get an idea of what would all possible functional observations for maybe new materials that we might want to explore. So we can get an idea of what are the all possible shapes that we might want to explore. Now let's think about this a little bit more. Now if we have, so think of functional experimental design, right? You would say, if my factor is functional observation, it's really hard to define what is my, my low value for my factor. So my minimum, my maximum, maybe like midpoints in traditional experimental design. But now I can convert that with FPCA to scores to get my two scores, right? Two scalar values that I can define highs and lows. I mean, we've already sort of explored that. So actually, if you try to do functional experimental design, JUMP has a platform that does this, and it will actually, this is what's happening in the background, is it's using functional PCA to redefine scores to alter your shapes for defining functional factors in DOE. All right, back to the analysis part. So how do we answer our question, right? Remember, we had the PC scores in 2 dimensions. So again, the typical approach, we'd just say, okay, k-means clustering. I picked 4. First component is 96.5% of our total variation. So it's no surprise that basically it's just 3 vertical lines to separate the 4 clusters. Our standard falls within green, and we kind of see the colored overlays here. And so to find the 3 closest, I just did the Euclidean distance between all the points and the standard and picked the top 3. They're all in the green cluster. And I think it's pretty cool picture here to show the raw data. So back to the discrete samples that were measured at the very first, the first picture, that black and the 3 green are extremely similar. And so, it might seem like I'd encourage anyone interested to look at the code, because basically once you have the functional object, it's only so smoothing plus PCA plus clustering. It's only a few lines of well-defined code. It's a pretty easy workflow to reach this result. So I actually think that this is a it was probably quicker than if I tried to do some of the other methods and trying to find different moments that would capture this shape appropriately. The last point on this is, so for the actual application that I applied this at Dow, we similarly selected, 3 similar materials based on this approach. And I think it was also a nice result that 2 out of those 3 were experimentally validated when they did more downstream work. So it was also a very successful project, and really the first time that it was applied within Dow at the time. So I'll definitely pause there for questions about FPCA.
Let me go over to the Slido, and I will just remind everybody again, if you just joined a little bit later, welcome. You are able to ask questions anonymously too, or through the YouTube live chat. So I'll just put the Slido link up there again as well. But one question that did come up a little bit earlier was specific FDA problems can pop up in my work, and I'm not always sure which analysis is right. Is there a recommended resource for selecting approaches?
Yeah, so there is a reference slide. So if you go, I'll probably pull it up, but may not talk about it when we get to it. But there's a series of 3 texts, all by slightly different authors, but Ramsey and Silverman are involved. And they're basically 3 different levels. There's one, it's a really small Springer book about just applications. So all those examples that I showed in the very beginning, it'll say, here's a type of problem or a type of data, and here's how you would solve it with a functional analysis method. So, and there some of them are pretty creative too. And so I think I would start there, because that gives you don't have to know anything about the code. That's the second one in the series. It's how do you do this in R or MATLAB? And then the third one is the full book, which has all the math and the derivations and theory. So it's a very easy read. That's all basically like, here's an application and here's how we might try and tackle it. So I think it's the, well, I guess we could skip to it real quick. So it's the third one on the list, applied functional data analysis. Typo, it's methods with a D and case studies.
I was trying to go and grab that link really quickly, but I will try and not do 2 things at once and do it after. Let me go over to YouTube and see what questions we have there as well. And here's one question that was from a little bit earlier too. Could FDA be used to describe sales of a certain product family?
I would say possibly. I don't know if we have enough information. So if product family is defined as, so something like what I'm showing of material characteristics where you have a functional observation, certainly you could have cost as an output. I mean, that's something that's commonly used for evaluating, like when you do an optimization of multiple properties, you could throw cost in and say, okay, how is, I want to optimize these application properties while minimizing cost, right? That's a typical approach. But I think it's hard to answer for sure without having, okay, where's the functional observation, or where's the functional data in that question?
Thank you. One other question that was on YouTube was, can you define functional as it is used in the FDA context?
Yes, simply that the underlying variable that you're trying to analyze is a smooth, continuous function, process, curve, distribution. So functional just refers to the type of data that we're analyzing. It's the equivalent of saying multivariate data analysis, where multivariate implies that you have more than one variable being analyzed at a time. Functional data analysis is you have functional data, and the methods, it's like the class of methods to analyze functional data. Curves, distributions, processes are the usual, just like a profile.
Awesome. Thank you. I just
Sure.
thought of a question here
Okay.
as well. So for people who are doing functional data analysis or connecting with each other, are there like typical resources that you use? Like, are you on a Slack group somewhere, or is there some community group somewhere?
No, at least not that I know of. Most of, like I say, I had the one class, and then the list or the essential library of textbooks out there is still pretty small. Like the list that I share of maybe 7 is like maybe 75% of the ones that I know about. So it's mostly self-learning. I do know like some universities have functional data analysis groups, but I don't actually follow. The authors of the text built a FDA website that is now defunct. So they tried to build a community, but I don't think it's not being maintained anymore. I think if you try to visit it. So unfortunately, yeah, it's kind of self-learning, exploring, and then as I meet new people who maybe do it at DAO, then we kind of make a community there, but nothing external for me.
Okay, I'll ask John Harmon over at the R for Data Science online learning community Slack if we can maybe just make a channel for it there too, so that at least
Yeah,
have a
definitely.
place for people to go to connect. I love the Slack channel or Slack community, so I put the link in the chat, and then I'll try and pull it up on the screen here as well.
It's good that Teams decided to, no, I don't want to join. Teams decided to disregard the fact I turned it off. That was nice.
No worries. Here, I just put that up if people want to check it out as well. And I think that's it for questions for right now.
Yeah, I see a couple pop up here. One about FPCA for 2 variables or maybe 2 dimensions. I'm sure I haven't explored those problems myself, but so within the refund package, I'd say that's newer and might tackle more. I mean, refund stands for regression of functional data, but there it also includes like functional PC regression is another approach that okay, this is fun, that they might actually tackle it there too. So again, I'd recommend, because I haven't done it myself, that some of the examples in those 3 books that I talked about might provide you some background on how you might handle 2-dimensional or multi-dimensional functional data type problems.
Great. I see a few more questions coming in now too, so let me pull them over to the screen. Which industries or sectors widely use FDA?
That's a good question. There is, so I don't remember off the top of my head, but there is a report. Maybe Rachel, I'll find it, and maybe we can share it somehow with everyone, because it actually does. It's like a systematic review of functional data across all industries. So they basically a few years ago went back, looked at all the literature where functional data was represented or referred to in keywords, and summarized it by method, industry, type of problem, and it was at least the only exhaustive list that I had found up to a few years ago, like I say. So is there a way that we can get that shared if I can find
Absolutely. Yeah. If you can find it after, I could put it with the recording as
Okay.
well. So this YouTube live link will immediately just become the recording right after the session today.
Okay.
And so I'll go and update the details with information.
All right.
Okay. Do you want me to hold a few more questions until the end, or
Yeah,
you want to take?
let's do that looking at
Okay.
time.
Perfect.
Because I do want to cover the functional regressions topic. So go back to my screen so I can progress. So before, just like we did with functional PCA, so what are different types of functional regression? It's not as straightforward as just like linear regression in terms of you can have functions on either side or both of your equation. So the first, scalar on function. You have a functional response and scalar variable, a single scalar in this case, as your input. I think it's easiest to look at in terms of functional ANOVA. Plus, it shows another analog to, sorry, another analog to a traditional method of just ANOVA. So the equation looks very similar, but you basically end up with an overall mean function, mean for your across all of your groups or your levels. And then you'd have a group specific contribution that's also a function. So just to give you an example with that Canadian weather data, again, you could look at the temperature or precipitation profile as a function of climate zone, which you would expect that, right, the contribution. So compared to the mean profile, if you're in the Arctic region, it's probably your contribution might be some negative function to drop your profile to be colder. For precipitation, if you're in the Pacific, it's probably wetter, for instance. So it's looking at your zone and trying to figure out what do the profiles look like as a function of your categorical input. Next is function on scalar. So just flip them. So now you have a functional input and a scalar response. And this is what we're going to apply in our situation here. And we'll see what the response looks like in a second. But I just always thought this equation was interesting because it's like the question first is how do you relate a scalar and a function? And so you actually estimate a slope function, which we'll see. And this slope function is represented as a basis expansion. So you actually use basis functions or basis expansion all over again when you actually fit this. So what do we do is we actually look at those coefficients because the basis functions are known. So the integral builds that relationship to convert the profile to scalar. So in the example, again, it'd be like predicting total precipitation based on temperature profiles. More generally, you could have function on function. So functions on both sides. Now you'd actually have a slope surface and the domains can be different. They don't necessarily have to be exactly the same. Of course, it gets more complex when they're different. And in the same example, it'd be now predict the entire prediction profile from temperature profile. And last is principal components regression, but functional version. So we'll actually see how we can use the results from our first exploration to predict our property. But now what's interesting and quite useful is right now it just becomes a essentially multiple linear regression in the for just a scalar response because we have uncorrelated scores that capture our variation. So it really does resemble what you do in regular principal components regression. To set the stage, so the true slope function that I have here is just like proportional to square root of time, and the reason being is because in general this property in the application that we're looking to predict, the further the curve is bounded away from zero, the slower the decay, the higher this property value. So since they all start at the same point, relatively small to no contribution at time zero, and you get a larger contribution as this is further away from zero and in longer time. So the responses are simulated again. All the code's available, and I just use the true exponential decay function, so no error, plus the true slope function, no intercept term, and so this is how we get the response. So I know I kind of leave out a lot of detail here, but we'll look at some more important, I think, or more interesting comparisons in a second. But just to give you an idea, so both of these perform similarly well. So we kind of expect that too. It's and maybe we'd hope so, because we capture nearly all the variability in the system with the functional PCA. So let's compare these two quickly. The functional linear model, I think one of the big benefits is you do get an estimate of that slope function. You don't do any dimension reduction, so you use the entire functional observation. And pre-smoothing is not necessarily always required depending on your inputs within the PFR function. So that's how you'd fit this within refund. Now, there are some cons, degrees of freedom, because the slope function is a basis expansion that you do have to worry about. If I use 10 basis functions, then that's 10 scalars that I'm estimating 10 degrees of freedom. So it can get, you can in some cases require a lot of data if you need a very extensive basis expansion for that slope function. Sometimes the slope function may not resemble the truth. I'll kind of show an example of that. And so it may not be guaranteed that you have a unique solution. So it's one that, while you can get the estimate, it's maybe use it with a grain of salt sometimes, because you can also, I've seen cases of just having large standard errors of my intercept, which you get good predictive performance, but I think it tends to being overfit in that case. So it just, I always recommend with the functional linear model, very careful exploration into model stability and standard errors and typical things we might look at in like a regression setting. And to show the example, so I actually do 10 different seeds, regenerate the response, and you can see the true function, slope function, is red. The solid black is from the original model fit, and we get a bunch of different lines with different slopes with the gray line. So you see some are steeper, some are flatter, but you also get some that are more quadratic. So they all have similar, maybe not exactly the same prediction performance, but it is possible that you could get a shape that's reasonable but slightly different from the truth. In functional PCR, I think it's easier just from a fitting standpoint and inversion, because we go back to just scalar scores. So which scores achieve a given property, and then we just apply that expansion to get the prediction, to get the function that is going to give us that predicted response. And again, this is all just tied to the amount of variation explained. So in this case, if we just looked at FPC1 only, we do lose some prediction performance, but we're only losing 3.5%. If PC1 was 50%, PC2 was 30%, PC3 was 10, you would expect very different performance if you just used PC1 only compared to all three. And one thing to keep in mind practically is, if you do this approach, you basically need, I would recommend, all the PCs for a given functional observation or none. Because if you just applied like model selection methods, what you'll end up seeing is that it might just say, oh, you only need FPC2. Well, that's only 3.5 out of our 100%. So you really need all of the more important PCs as well. So if you pick 3, use all 3. All right, I will, in the interest of time, I will go to the second comparison. So just to compare to, or to kind of show how I think functional regression, it can be so powerful. Scenarios where you have more of a wide matrix, so far more columns than rows. So in this case, I simulated 10 materials, but now everything's measured at every hour. So it's a 10 by 25 matrix. We can apply various methods. So I can compute moments like numerical derivatives and just apply regression. So just rise over run, either the entire domain or subsections, bins. I can look at area under the curve, right? The larger that area, the further from zero. It's a natural moment to pick. I can do just regular PC regression on the data matrix. I can estimate, say, oh, I think exponential decay is appropriate here. So let's estimate that parameter. Then we know everything, and just use that as our moment. And what you see is, compared to the functional methods, moment-based approaches, we just lose too much information typically. And even if multivariate approaches perform similarly, we still lose that functional relationship. So I think this is a powerful example to show that in very data limited scenarios, we actually can apply and use the entire function in regression or like PCA settings. So I see we're right at time. I will just leave the takeaways and further thoughts up here, and ask or happy to answer questions. Rachel, if you are allowing this to extend, I'm happy to stay in chat. If it needs to end, I'll let you make that
Yeah,
call.
if you're able to stay and chat with us, that's awesome.
Yeah.
Great. Yeah, there's a few other questions I know from a little bit earlier. And one was from Santiago. And I will say I have learned a lot of acronyms through this meetup and Googling, but between FPCA, then K-means on the PCs versus functional clustering techniques, such as FunFem, which, Santiago, that sounds fun. I just asked what that means. Any thoughts around how to choose between the two approaches?
Yeah, I have the same question. I've not seen FunFem before.
I wish I could bring you on here, but unfortunately with the platform, I can't bring people on to chat.
Yeah, so I guess that one I'd have to look up, or if you could send in the chat what FEM there stands for. Yeah, so I can't, I guess, answer the question.
No worries. Yeah, we can save that one for later. Another question was, is there some sort of an overlay between functional data analysis and time series?
Yeah, and so actually that gets to a potential like takeaway here that I didn't actually talk about when I was covering smoothing. But so the data can be very related, right? You look at, we have measured points over time in our case study. It looks like you could do something with time series. However, that key limitation, time series is very rigid about needing equally spaced points, and if you have multiple different series, that they have the same number of points. um, what you could do is actually use smoothing as like an imputation approach, or a way to convert data like our case study, which I did in an earlier step, right? I smoothed all of them, then I reevaluated at every hour from 0 to 24. So what did I essentially converted them all to equally spaced and same number of time points. So that's actually one approach that I think can be used if you, um, provided, of course, that the smoothing is able to capture the, like it's not such a complex time series that just a smoother can't give you reasonable estimates for where you're trying to interpolate. But as long as it's reasonable, I think you could use smoothing as a precursor to time series, because remember, time series and FDA might actually solve different problems too. So if you're looking at time series to analyze stationarity or seasonality, that's a different type of question being answered than like the clustering or prediction in functional data. I'd use time series for forecasting, for instance. There are approaches you could do in FDA with forecasting, but I think if I could use time series, I would.
Awesome. Thanks, Matt.
Yep.
Another question that was over on Slido is, have you tried your example with traditional PCA or PLS? And can you just, for everybody here, just explain those acronyms as well?
Sure.
Any comparison on how FDA performs better or worse?
Yeah, so I think the big difference, so right, PCA is principal components analysis and PLS is partial least squares. The difference between those two is PLS, you actually have a response or set of responses. So like PCA is dimension reduction on a data matrix that's typically then like you might not have a response. PLS says I want to use that. I want to reduce dimension on the input space, reduce dimension on the output space, and relate those two together. The big limitation of PLS, and it's actually in a paper that compares these two. It does that example of functional observations say that column 1 is related to column 2 to column 3 based on that function, right? So if we did a data matrix of decay, we would see that the values should decrease as you move left to right in the table. The columns are all related in a specific fashion, a specific order. That's the functional piece of this. In PLS or PCA, it doesn't care which column is where. You could just randomly permute those columns, just mix them all up, and you would get the exact same model. So I think you could see cases. So like for instance, if I go into the other example I was going to share, here's an example where principal components regression technically does outperform in terms of smaller prediction error than a functional method. However, I would argue that if I have functional data, I would actually want to use that information in my analysis. So even though PCR does better, I still gain way more interpretation, actual contextualizing the solution, the problem from FPCR and FLM than I would PCR. PCR being principal components regression.
I'm learning them. Awesome. Thank you. I just want to double check. Were there any questions that I have missed? And if so, feel free to repost in the YouTube chat as well. I don't see any others on Slido. Let me just double check. And thank you so much, Matt, for sharing this with us and giving us this introduction. This is very helpful and really fun to start to think of all the ways it can be applied in other industries too.
Yeah, I think that was, continuing the story, another sort of just happy coincidence was there's just a lot of examples of functional data within plastics and within the business where I was working in. And so it was lots of questions that needed to be answered. And the team didn't know how to do it. And I was like, hey, I learned this thing, this functional data analysis set of methods. I was like, well, why not try it? And that actually just led to more projects, more exploration. And that was simply just a meeting with, as a new employee with a senior fellow who had some ideas and just looked at the data and said, oh, let's try something different. And just, the rest is history, I guess.
That's great. Thank you so much. And thanks for reaching out after the first meetup you came to and wanting to continue this series on as well. Hopefully we can find some way for everybody to connect further to talk about this as well. I did
that'd be great.
Reach out on the R for Data Science online learning community too to see if we could create a channel there. But you can also connect with people through the meetup recording, which will automatically be on YouTube. And we'll put all these helpful resources that have been shared there as well. Also, just want to remind everybody, if you are here today and are thinking about, oh, I just learned this really cool thing, or I want to share a use case too, I would love to talk to you. And I'll put my LinkedIn in the chat right here. If you just want to reach out and say hello and maybe share a few of your ideas, would love to meet you there too. But thank you so much, Matt. Really appreciate your time today.
Thank you. And thanks everyone for joining.
Have a great rest of the day, everybody. Thanks for joining.